As we wrap up this lesson on 2.4, I want to introduce you to a few other phrases that people in the real world, in real contexts, in different industries, in different jobs will use when they actually are meaning derivative. So I just want you to be familiar that these phrases have the implication of using the derivative to answer them, talking about rate of change, but what different industries might refer to it as being synonyms. So we're going to talk about those other phrases today. So we're familiar with the idea of rate of change with the word instantaneous. You should recognize that this is the way Newton did it. So we have so many different ways of things that mean derivative. We've talked about velocity, we've talked about tangent, we've talked about slope of a curve. All of these synonyms meaning the instantaneous rate of change, and all of them being done with the derivative rules that we've established this chapter. We can talk about delta. Okay, the expected change delta. You might see that in science, different a lot of chemistry examples, maybe a lab in a biology thing, or human anatomy. They talk about what's the delta, what's the change. They're really talking about what's the derivative. And so again, just be expecting when you see that the delta is actually the Greek letter delta looks like this. And so that's actually where we get our modern letter D from, which is why Leibniz used that. When he talked about delta, he abbreviated with D, and so that's where we get the D in our derivative notation for from Leibniz. So we can apply our derivative rules to other areas of math, other areas of science. Let's see what it looks like in geometry. If we are given an area function, so you should recognize this as being the area of a circle, dependent on the radius r. If we're asked to find the rate of change with respect to the radius r, so the radius r is the variable. What we want to remember is that pi is not a variable. Pi is a constant, same as the number 5 would be a constant, or the number 13. Pi is a constant. So if we want to find the rate of change of the area with respect to r, so we're going to use Leibniz's notation to write that. So we'll say d, which is going to be the rate of change or the derivative of the area, so dA over, and then with respect to radius r, we're going to do dr. So it's dA over dr. That is the common notation to write when you talk about the rate of change, and we're talking about a geometric expression. Now we use the regular rules to do it. So our regular rule we're going to do is the power rule. So as we look back over this expression, we want to recognize the power of 2, which is going to get pulled in front. Now remember, pi is a constant, so that doesn't play into the derivative at all. So it's going to come out as 2 in front of the pi, and now r is going to be decreased down to the value of 1. And so if we simplify that, we get 2 pi r. Now I want you to notice we started with a geometric expression in area, and hopefully that 2 pi r is a trigger for you're like, I have 2 pi r. Where have I seen that before? 2 pi r is the circumference formula. And this is not a coincidence. It is not a coincidence that the derivative of the area formula results in the circumference formula. These things are all connected. They're all related, and calculus explains it all. So in elementary school, when they tell you, or in middle school, upper middle school, they tell you, here's the formula for the circumference of a circle. It's 2 pi r. And I don't know how many of you ever asked, why is it 2 pi r? How do you know it's 2 pi r? Same thing with the area. Here's the formula for the area, pi r squared. Well, how do you know that's the formula? And you say, well, it just is. It just works. Calculus is what proves that the area, which is a two-dimensional representation, the derivative of that turns into the circumference. All right, next we want to evaluate the rate of change when R is 4. And so we're going to say dA dr when R is 4. Or another way to write that would be A prime when R is 4. So that would be 2 pi plugging in the number 4, and we get the value of 8 pi. Now, the next thing is find the expected change in A. So this is really interesting. The expected change of A is different than the rate of change, or the instantaneous rate of change. The expected change in A is defined as getting just the dA part alone. That's the expected change. How much will the area change if we change R by a little bit? So we want to get dA alone. So if we have the equation dA over dr equals 2 pi r, if that's our formula from part A, and we want to get dA alone, we're going to drop a 1 under here, and we will cross multiply. And so when we do our cross multiplication, dA is going to come down, so we'll have dA. And then when we cross multiply the other direction, we will end up with dr times 2 pi r, or we write that as 2 pi r, and then with a dr on the end. Dr is a whole quantity together. It's not d separate from r. Dr kind of goes together. Maybe you want to put parentheses around that or something to simplify those together. So the expected change in A, if r is changed by 0.5, that doesn't say r is 0.5. It says that r is changed by 0.5. And so the changed by 0.5 is the delta r, or the dr. So that goes in here. So we have 2 pi times r times 0.5, which simplifies to be 1 pi r. So the change in r, just keep watching that. R isn't 0.5, r is changed by 0.5, and so that's a delta r. So dr is actually equal to 0.5. Now, we talk about sensitivity, and that means how much something impacts you, or how much it impacts a number. If we change something a little bit, does it have a resultant big change or small change? Is it highly sensitive or not really very sensitive? We all know people in our lives that what we would call, oh, you're a sensitive person. That means maybe a small thing would really make them very, have a big emotional reaction to that. So in math, same thing. We talked about things being sensitive. We can measure this with calculus. And sensitivity is another word for derivative, and it's the separation. So df or dx by itself is the sensitivity. So dA would be the sensitivity of A. dr would be the sensitivity of R. How much will one change impact another change? So if I were to change A, how much would that change R? Or if I were to change R, how much would that change A? How are they related and connected? So the word sensitivity is connected to derivatives, but it's a separation where we can look at them independently of each other, dA being separated from dr. We can use this. Give me an example of an agricultural situation. So let's examine, let's pretend we're out in Nebraska, out in the fields or whatever, in the belt of the Midwest, and our crop is dependent on how much rain we get. And so we could say this, we would read that as the derivative of C with respect to R. In other words, the crop depends on, or if we change the crops, the change in the crops, whether the crops change in a positive way or whether the crops change in a negative way, whether the crops really grow well or whether the crops shrivel up and die, is dependent on the amount of rainfall we have. And so if you want to look at how sensitive the crop is by itself, you cross multiply and you get DC alone, and then you get KR times DR. And so you've just separated that. You can figure out how much the crop itself, the dependency of the crop, is to the rainfall itself. You can do the same thing in medicine or medication for a drug, and you want to lower a patient's temperature. We can say that the temperature, which is measured by T in this equation, depends on how much of the drug that they're prescribed, how strong of the drug it is, how many milligrams they take, how much of the drug X will work. But if we want to know how much the temperature will change, we want to get dt alone. So we do a cross multiplying again, and that would give us dt times X, and then K is multiplied by the dx, but that doesn't quite get me dt alone. So dt by itself would be K times dx. Sometimes it's helpful to keep that as a quantity over X. And that will help me figure out, all right, if I give them an amount, so that would be the amount. The dx is going to be the change in the amount. And then K would be a given constant. So we'd be given that to plug that in. We could do the same thing with the rainfall question. Okay, if we're looking at the rainfall, we know that R is the amount of rain. dr is the change in the amount of rain. So maybe, okay, we got 2 inches. That would be the amount of rain. And we're expected to get a ½ inch more. That would be the change in the amount of rain. And then you'll have a constant here that you would be given to use. So just understanding the vocabulary and what it's asking. You can also use derivatives in the field of economics. In economics, they call derivatives marginals. It's just the word that they use in the study of economics because a marginal is a small change in something. The change is marginal. It's very small, and we measure that change with derivatives. So when they ask about marginal, they say, what is the cost of production and what is the marginal cost of production? One of them is C of X, and the other one is C prime of X, or we can write it in Leibniz notation, dC dx. Also, those are the same thing. So marginal means using the derivative to find that. Using the derivative to predict, what's the expected change in this economic situation? If the cost is based on something, and what would our expected change of cost be? All of those things are based on derivatives as well. So when you see these problems in your homework, just know that you'll be using the derivative when you're talking about sensitive questions, when you're talking about change questions or expected change questions, and when you're talking about marginals in economics, the marginal cost, the marginal revenue, the marginal production, all of those, that would be a word that would be meaning use the derivative as well. All right, we'll talk more about this next week when we're back together.